Picture a world so vast it could swallow every other planet in our solar system and still have room to spare. A swirling giant of hydrogen and helium, wrapped in storms larger than our entire planet, where winds scream at speeds that defy comprehension. This is Jupiter, not just a planet, but a cosmic enigma that has fascinated astronomers for centuries. Even after decades of robotic explorers and telescopic observations, it remains a place of profound mystery, a celestial puzzle begging to be solved. What secrets lie beneath those turbulent clouds? Why does this colossal world behave in ways that constantly upend our expectations? Think about this for a moment. Jupiter's gravitational pull is so immense that it acts like a cosmic shield, deflecting asteroids and comets that might otherwise threaten Earth. It's been called the solar system's guardian, a silent sentinel standing between us and chaos. But for all its protective power, Jupiter harbors riddles that even our most advanced science can't fully explain. Towering storms rage for centuries, yet no one knows exactly how they form or why they persist. Deep below the clouds, scientists suspect a colossal core of exotic matter, except the evidence suggests it might not even exist. How can a planet so massive defy the very laws we thought governed planetary formation? That's where this journey begins. Today, we're diving into 25 of Jupiter's most baffling mysteries, phenomena that challenge our understanding of physics, weather, and even the origins of our solar system. From the churning chaos of the Great Red Spot to the eerie silence beneath its magnetic storms, each mystery pulls us deeper into the unknown. So if you've ever stared up at the night sky and wondered what truly lurks within those distant bands of gas, you're in the right place. By the end of this exploration, Jupiter won't just be a bright dot in the sky, it'll be a world of endless wonder, waiting to reveal its secrets. Let's begin. The Great Red Spot stares back at us from Jupiter's surface like a colossal, unblinking eye, a storm so vast it could swallow Earth whole. This swirling vortex of crimson gas has churned non-stop for at least 400 years, possibly longer. Think about that. While hurricanes on Earth fizzle out in days or weeks, Jupiter's most famous tempest has outlasted empires, outlived generations, and defied every rule we know about how storms behave. What keeps it spinning with such relentless fury? Scientists suspect the answer lies in Jupiter's chaotic atmosphere, where jet streams race at over 300 miles per hour, channeling energy into the storm like cosmic fuel lines. But here's the twist. Unlike Earth storms, which draw power from warm ocean waters, the Great Red Spot has no obvious energy source. Some researchers believe heat welling up from Jupiter's scorching interior acts like a hidden battery feeding the storm's rage. Others argue it's all about momentum. The spot might be a self-sustaining engine, trapping swirling gases like a celestial whirlpool that never drains. Yet, even as we try to unravel its secrets, the Great Red Spot is changing. Over the past century, it's shrunk by more than half, morphing from an oval wider than 3 Earths to a tighter, more circular range. Some fear it could vanish entirely within our lifetimes, while others speculate it's simply evolving into something new. One thing's certain: whether it grows or fades, this ancient storm holds clues to Jupiter's deepest mysteries: how energy moves through its atmosphere, how its layers interact, and perhaps even how such colossal storms birth themselves in the first place. The real shock: the Great Red Spot might not even be unique. Recent telescope observations reveal other, smaller storms flaring up across Jupiter's bands, some merging, some fading, all hinting at a turbulent world where violence is the norm. If we can crack the code of this crimson giant, we might finally understand why Jupiter's weather operates on a scale and timeline unlike anything else in our solar system. Jupiter's interior holds one of the most baffling secrets in planetary science. It might be missing its core. For decades, astronomers assumed this gas giant harbored a dense, rocky heart, similar to Earth but scaled up to 20 times our planet's mass. That assumption made perfect sense. After all, how could a planet 11 times wider than Earth form without some solid anchor at its center? But when NASA Juno spacecraft began measuring Jupiter's gravitational field in 2016, the data told a very different story. Instead of revealing a compact core, Juno found evidence of something far stranger, a diffuse, fuzzy region where heavy elements might be dissolved like salt in water, spread across nearly half the planet's diameter. What could possibly erase a planetary core? The answer may lie in Jupiter's nightmarish interior conditions. Imagine pressures so intense they crush hydrogen into a metallic fluid, temperatures hotter than the sun's surface, and chemical processes we can't replicate in any laboratory. Some scientists believe Jupiter's original solid core didn't disappear, it melted. Over billions of years, the staggering heat and pressure may have eroded the core's boundaries, blending its material into the surrounding soup of liquid metallic hydrogen like a sugar cube dissolving in tea. Others propose an even wilder idea. Jupiter might have formed through a violent collision with another protoplanet early in its history, shattering its core into fragments that gradually dispersed. This isn't just academic curiosity. Jupiter's core crisis forces us to rethink how planets are born. The traditional core accretion model, where dust clumps together to form a solid center before attracting gas, suddenly seems incomplete when applied to our solar system's largest world. Could Jupiter have formed through gravitational instabilities in the primordial solar nebula, collapsing directly from gas without a solid seed? The debate rages on, with each new Juno data drop adding fresh twists. Perhaps most unsettling is what this means for other gas giants. If Jupiter lacks a defined core, what does that imply about Saturn, Uranus, or the countless exoplanets we've discovered? We're left staring at a cosmic paradox, a planet so massive it bends light and deflects asteroids, yet somehow defies the very rules we thought governed planet formation. Until we send more probes into its swirling depths or simulate those impossible pressures in labs, Jupiter's missing core will remain one of the solar system's greatest unsolved puzzles. Jupiter's auroras paint its poles with light shows that make Earth's northern lights look like faint candle flames. These dazzling displays aren't just beautiful, they're the most powerful auroras in our solar system, pumping out energy at levels that would vaporize entire cities if unleashed on Earth. But here's what really baffles scientists. While Earth's auroras are powered by solar wind particles colliding with our atmosphere, Jupiter's light shows rage with such intensity that the solar wind alone can't possibly explain them. Something far stranger is at work here. For starters, Jupiter's northern and southern lights don't follow the planet's rotation like clockwork. They pulse to their own erratic rhythm, sometimes flaring up independently of the solar wind's ebb and flow. Then there's the bizarre, dark region near the North Pole where auroras completely vanish, creating a mysterious void in an otherwise continuous light show. Even more perplexing, these auroras generate X-rays, something no other planet's light shows produce, with enough power to briefly outshine the sun in certain wavelengths. The likely culprit, a cosmic game of tug-of-war involving Jupiter's volcanic moon Io. As Io spews sulfur dioxide into space at nearly 2,000 pounds per second, Jupiter's immense magnetic field rips these particles away, creating a donut-shaped plasma torus around the planet. When these charged particles spiral along magnetic field lines toward the poles, they might be supercharged by unknown processes, creating auroras up to 30 times more energetic than Earth's. Yet even this explanation leaves gaping holes. Some auroral flares erupt when Io isn't in the right position to feed them particles, suggesting hidden energy sources deep within Jupiter's complex magnetic field. Others appear linked to unexplained magnetic reconnection events, sudden rearrangements of magnetic field lines that release bursts of energy like snapped rubber bands. The truth might lie in Jupiter's turbulent interior, where swirling oceans of metallic hydrogen could be generating electric currents powerful enough to light up the sky from within. Every new observation raises fresh questions. Why do Jupiter's X-ray auroras sometimes pulse like a cosmic heartbeat? How can part of the auroral zone remain completely dark while surrounding areas blaze with intensity? Until we solve these riddles, Jupiter's light shows remain both a spectacle and a scientific enigma. Nature's most brilliant mystery written across the polar skies of a gas giant. Jupiter's magnetic field shouldn't be this weird. Every textbook will tell you that planetary magnetic fields should be roughly symmetrical, a nice, orderly force field generated by the churning of electrically conductive fluids deep inside a spinning planet. But when NASA's Juno spacecraft mapped Jupiter's magnetism in detail, it revealed a cosmic oddity. The northern hemisphere's magnetic field is radically different from the southern one, as if someone took a perfectly balanced system and smashed it with a sledgehammer. Take the so-called Great Blue Spot, not an atmospheric storm, but a bizarre concentration of magnetic energy near Jupiter's equator that looks like a bruise on the planet's invisible force field. This patch of intense magnetism drifts eastward at about 4 centimeters per year, stubbornly refusing to sync up with Jupiter's rotation or follow the patterns we'd expect from fluid dynamics. Meanwhile, the entire northern magnetic field appears disorganized, with chaotic patches of magnetism that resemble a Jackson Pollock painting rather than the neat lines seen in Jupiter's southern hemisphere. What could cause such dramatic asymmetry? Earth's magnetic field comes from motions in its molten iron outer core, a relatively straightforward process. Jupiter, by contrast, might be generating its magnetism in an ocean of metallic hydrogen so deep and pressurized it behaves like nothing we've ever studied. Some researchers think Jupiter's lopsided field hints at zones where this exotic fluid is rising or sinking with unusual violence, creating turbulent pockets of magnetic energy. Others speculate that the planet's rapid rotation, spinning once every 10 hours, somehow twists the magnetic field into these strange configurations, like taffy being pulled in different directions. The implications are staggering. If Jupiter's dynamo operates by different rules than we thought, it could rewrite our understanding of how magnetic fields form not just in gas giants, but in exoplanets across the galaxy. Even more puzzling, similar asymmetries have been spotted at Saturn, suggesting this might be a common feature of gas giants that our models simply fail to predict. Until we can peer deeper into Jupiter's swirling interior or replicate these conditions in supercomputer simulations, the mystery of its lopsided magnetism will remain one of the solar system's most confounding physics puzzles. Jupiter should be freezing. At its distance from the Sun, this gas giant receives only about 4% of the solar energy that bathes Earth, just enough to keep its cloud tops at a frigid -230 degrees Fahrenheit. But when scientists measured the planet's total heat output, they got a shock. Jupiter radiates almost twice as much energy as it absorbs from sunlight. This means something inside the planet is cooking at temperatures that defy simple physics, pumping out enough extra heat to power a second sun. Where is all this energy coming from? One leading theory points to Jupiter's violent birth. When the planet formed 4.5 billion years ago, countless comets and asteroids likely smashed into its surface at terrifying speeds. The energy from those impacts plus the heat generated as gravity compressed Jupiter's gases might still be slowly leaking out, like a cosmic oven gradually cooling after a marathon baking session. But here's the problem. Calculations show this primordial heat should have dissipated billions of years ago. For Jupiter to still be this warm, there must be an ongoing energy source stoking its internal furnace. That's where helium rain comes in, a bizarre weather phenomenon possible only in the extreme pressures of a gas giant. Deep beneath Jupiter's clouds, where hydrogen behaves like liquid metal and pressures exceed 2 million times Earth's atmosphere, scientists theorize that helium might condense into droplets and fall like rain. As these super-dense helium droplets sink through lighter hydrogen layers, friction would generate tremendous heat, like rubbing your hands together but on a planetary scale. Some models suggest this process could explain up to half of Jupiter's unexplained warmth. Yet even this elegant solution comes with complications. Recent measurements reveal the planet's heat isn't distributed evenly. Certain latitudes glow much brighter in infrared than others, creating mysterious hotspots that current models can't explain. Then there's the puzzling observation that Jupiter's excess heat seems to pulse over time, fluctuating in ways that suggest an invisible thermostat at work. Could electrical currents in Jupiter's metallic hydrogen core be acting like a giant space heater? Might slow gravitational contraction, the planet gradually shrinking by about 1 inch per year, be squeezing out extra energy like a cosmic stress ball? The implications stretch far beyond Jupiter. If we can't fully explain the heat budget of our solar system's largest planet, how can we accurately model the thousands of gas giants orbiting distant stars? This thermal mystery forces us to reconsider basic assumptions about planetary evolution, energy transfer, and the hidden dynamics of gas giant interiors. Until future probes can peer deeper through those swirling clouds, Jupiter's unexplained warmth remains a glowing reminder of how much we still don't understand about the giants roaming our cosmic neighborhood. Jupiter's poles are home to a meteorological circus unlike anything else in the solar system, where cyclones arrange themselves with near-geometric precision, defying every expectation of how storms should behave. When NASA's Juno probe first captured close-up images of these regions, scientists stared in disbelief. At the North Pole, 8 massive cyclones spin in a perfect octagonal formation around a central storm, while the South Pole hosts 5 hurricanes locked in a rigid pentagon. Each of these tempests is wider than the continental United States, yet they maintain their positions with eerie stability, like dancers in some cosmic ballet that's been performing for centuries without missing a step. This orderly chaos poses a fundamental puzzle. On Earth, hurricanes that get too close either merge or push each other away. But Jupiter's polar cyclones refuse to follow these rules. They orbit their central storms at fixed distances, their outer edges sometimes coming within 800 miles of each other, close enough to share swirling cloud bands, yet never combining or breaking formation. Some researchers compare them to repelling magnets held apart by invisible forces we don't yet understand. Others suggest the answer lies in a phenomenon called the beta drift, where Jupiter's rapid rotation creates atmospheric highways that guide storms into stable orbits around the poles. What really bends the mind is how these cyclones maintain their energy. Earth's hurricanes dissipate once they move over land or cold water, but Jupiter's polar vortices have no such obstacles, just an endless supply of warm gas rising from the planet's interior. Computer simulations show these storms should either collapse or merge within years, yet observations prove they've persisted unchanged since Juno's arrival in 2016. Some theorists propose the cyclones tap into deep-rooted jet streams we can't yet observe, while others wonder if electrical currents in Jupiter's atmosphere play an unexpected role in stabilizing the system. The most tantalizing clue comes from the geometric spacing itself. The angles between cyclones match mathematical models of vortex crystals, hypothetical arrangements where swirling fluids self-organize into symmetrical patterns. On Earth, we see faint echoes of this behavior in the spacing of ocean eddies, but Jupiter takes it to an extreme that shouldn't be possible at such massive scales. If we can crack the code of these perfect storm polygons, it might revolutionize our understanding of fluid dynamics across the universe, from Earth's weather to the swirling atmospheres of distant exoplanets. Until then, Jupiter's polar cyclones remain one of nature's most mesmerizing demonstrations of order emerging from chaos. When you picture planetary rings, Saturn's dazzling ice bands probably come to mind, great shimmering hoops that catch sunlight like cosmic jewelry. But Jupiter's rings are another story entirely. They're so dark and faint, they weren't even discovered until 1979, when Voyager 1 spotted them by sheer accident. Unlike Saturn's reflective ice, Jupiter's rings are made of dust so charcoal black it absorbs almost all light that touches it. If you stood within these rings during daylight, you'd barely notice them, just a dim haze stretching into the gloom like smoke lingering after a fire. What makes these shadowy rings even stranger is their origin. Saturn's icy loops come from shattered moons or ancient comet debris, but Jupiter's rings seem to be constantly replenished by something far more violent. Micrometeorites relentlessly pound the planet's four inner moons, Adrastea, Metis, Amalthea, and Thebe, blasting dust off their surfaces with each impact. Jupiter's colossal gravity then captures this debris, stretching it into those ghostly rings we see today. It's a demolition zone on a planetary scale, where moons are slowly disintegrating to feed an ever-shifting halo of cosmic soot. Yet the real mystery isn't just why these rings are dark, it's why there's so little material there at all. Jupiter's gravity should theoretically trap far more dust, creating rings rivaling Saturn's in thickness. Instead, they're whisper-thin, barely clinging to existence. Some researchers think Jupiter's magnetic field acts like a giant vacuum cleaner, sucking charged particles out of the rings and flinging them into space. Others propose that the same impacts creating the dust also blast it away, like a ceiling fan scattering smoke. There's even a wild theory that invisible, shepherding moons might be stealthily sweeping the rings clean, though no such objects have been found. The most haunting possibility, Jupiter's rings might be temporary. Without constant replenishment from those beleaguered inner moons, they'd vanish within decades. If impacts ever stop, or if those moons crumble entirely, this faint Gothic halo could disappear as quietly as it formed, leaving future astronomers to wonder if it was ever there at all. Jupiter's striped appearance isn't just for show. Those alternating light and dark bands tell the story of an atmosphere in constant, violent motion. Like Earth's jet streams but cranked up to absurd extremes, these bands are actually high-speed winds racing in opposite directions, some exceeding 400 miles per hour. But unlike Earth, where mountains and landmasses slow winds down, Jupiter's jet streams face no such obstacles. With no solid surface to create friction, these atmospheric rivers plunge hundreds of miles downward, turning the planet into a layered cake of tempests that behave unlike anything in our solar system. The light-colored zones are where gas rises, cooling and forming bright ammonia ice clouds. The darker belts, by contrast, mark sinking air, warmer and drier, with complex chemistry that gives them their tawny hues. What's astonishing is how deep these patterns go. NASA Juno spacecraft revealed these jet streams penetrate at least 2,000 miles below the cloud tops, reaching depths where pressures are so intense, hydrogen acts like a bizarre metallic fluid. That means Jupiter's stripes aren't just skin-deep weather. They're windows into the planet's churning interior, hinting at energy transfer mechanisms we're only beginning to grasp. Here's where the mystery deepens. On Earth, jet streams meander and shift with seasons, but Jupiter's bands are eerily stable, locked in place for centuries. Even more puzzling, the planet's equator hosts a superfast jet stream blowing eastward, while higher latitudes alternate between east and west, flows like a meticulously arranged atmospheric zebra. Computer models struggle to replicate this precision without surface friction or seasonal changes. There's nothing obvious to maintain this rhythmic chaos. Some scientists suspect convection deep within Jupiter. Heat rising from its core acts like an invisible hand, orchestrating these flows. Others point to the planet's rapid rotation, which might create a planetary-sized version of the Coriolis effect, amplifying wind shear to unimaginable extremes. The real shock came when researchers realized these jet streams might be connected to Jupiter's interior in ways we never anticipated. Magnetic field data suggests the deep winds could be influencing, or even being driven by currents in the metallic hydrogen layer below. Imagine if Earth's trade winds were somehow linked to motions in our molten outer core. That's the level of complexity we're dealing with, until we understand how energy propagates through thousands of miles of swirling gas. Jupiter's banded beauty will remain one of its most mesmerizing enigmas, a cosmic fluid dynamics experiment operating on a scale beyond human imagination. Jupiter's atmosphere holds a secret that shouldn't be this complicated: water. Not liquid oceans or icy glaciers, but water vapor mixed into those swirling bands of gas. You'd think measuring something as familiar as H2O would be straightforward, yet the numbers from our spacecraft tell two wildly different stories. When the Galileo probe plunged into Jupiter's clouds in 1995, it found a desert water level so low they barely registered. Fast forward to 2017, and Juno's microwave measurements painted the opposite picture: pockets of atmosphere drenched in water, some regions holding 3 times as much oxygen as the Sun. How could two reliable missions deliver such contradictory results? The answer might lie in Jupiter's turbulent weather. Unlike Earth, where water distributes relatively evenly, Jupiter's atmosphere behaves like a cosmic blender, some areas bone dry, others drowning in vapor. The Galileo probe sampled just one location, descending into what scientists now suspect was an atmospheric desert, a freakishly dry spot where downdrafts might have sucked moisture deep below the clouds. Juno, by contrast, scanned broad swaths of the planet using microwave radiometry, revealing that water isn't mixed uniformly but clumps in unpredictable wet and dry zones. Imagine if Earth had rainstorms over Miami while the Sahara flooded, but the Mediterranean stayed parched. That's the kind of uneven distribution we're dealing with on Jupiter. But here's where it gets stranger. Even Juno's data shows bizarre inconsistencies. The planet's equator appears significantly drier than the mid-latitudes, while the Great Red Spot of all places acts as a surprising reservoir of moisture. Some researchers think Jupiter's water isn't just sitting in the atmosphere. It might be cycling through layers we can't see, welling up in some regions and vanishing into the depths in others. Others speculate that cometary impacts periodically dump water into the atmosphere, creating temporary wet zones that gradually dissipate. The implications ripple far beyond Jupiter. Water abundance is a key clue to how and where the planet formed. If Jupiter really is richer in water than we thought, it might have been born farther out in the solar system, where icy debris was plentiful before migrating inward. Alternatively, the dry measurements could suggest most of its water remains locked beneath the clouds, hidden in layers we've yet to probe. Until we send another mission capable of sampling multiple locations or peering deeper into the storm layers, Jupiter's water mystery will keep us guessing, a reminder that even the simplest questions can defy explanation when dealing with a planet this unpredictable. Lightning on Jupiter doesn't play by the rules. While Earth's lightning bolts crackle through thunderstorms in predictable patterns, Jupiter's electrical outbursts erupt in ways that baffle scientists. Imagine bolts up to 3 times more powerful than anything on our planet, flashing not just in storm clouds but near the poles, places where lightning shouldn't exist at all. Even stranger, these discharges pulse at frequencies far higher than Earth's, creating a thunderstorm symphony tuned to a pitch we've never heard before. The first clue to this puzzle lies in what fuels these otherworldly bolts. On Earth, lightning forms when ice crystals and water droplets collide in storm clouds, generating static charges. Jupiter's atmosphere, though, is far too cold for liquid water clouds at the altitudes where lightning typically sparks. Instead, researchers suspect a slushy mixture of ammonia and water acts as Jupiter's electrical engine. At certain depths, ammonia gas may dissolve into water vapor, creating a bizarre, conductive cocktail that churns inside storm systems. When this ammonia-water solution freezes and shatters, the fragments could collide like hailstones, building up charges until the sky erupts in flashes visible from space. But location makes this mystery even weirder. Most of Jupiter's lightning concentrates near its equator until you notice those eerie polar flashes. Earth's poles rarely see lightning because they lack the heat-driven convection that powers storms. Yet Jupiter's high latitudes crackle with electrical activity, especially during periods of intense auroras. Some scientists theorize that charged particles from the Sun, funneled by Jupiter's monstrous magnetic field, might seed these polar storms. Others propose that convection near the poles works differently, with heat from the planet's core driving violent updrafts through layers of ammonia-rich clouds. Then there's the rhythm of the strikes themselves. While Earth's lightning flickers in milliseconds, Jupiter's bolts can last a full second or longer, slow, rolling discharges that crawl across the sky. Spacecraft have even detected superbolts with energy signatures unlike anything in our weather databases. These could stem from discharges between layers of clouds separated by vast distances, or from exotic forms of plasma we don't yet understand. What truly unsettles researchers is how these discoveries force us to rethink the very nature of lightning. If ammonia-driven storms can generate such colossal sparks, what might be happening inside the atmospheres of even more extreme exoplanets? Jupiter's defiant lightning isn't just a spectacle, it's a challenge, daring us to expand our understanding of how electricity behaves in conditions beyond anything our planet can offer. High above Jupiter's churning cloud tops, where the atmosphere thins into space, scientists have stumbled upon something that defies all expectations: a colossal, cold spot, hanging like a shadow in the upper atmosphere. This region, chilling to -200 degrees Fahrenheit, is over 7,000 miles wide, yet it lingers stubbornly in the thermosphere, a layer that should be searing hot from solar radiation and auroral activity. What makes this icy anomaly even stranger is that Jupiter's upper atmosphere is constantly churned by violent winds. So why hasn't this frigid patch been erased by the planet's relentless mixing? One leading theory points to a cataclysmic event from the past, the crash of comet Shoemaker-Levy 9 in 1994. When this fragmented comet slammed into Jupiter, it released energy equivalent to millions of nuclear bombs, possibly punching a temporary hole in the upper atmosphere that never fully healed. Like a scar in the sky, the cold spot might be a lingering thermal fingerprint of that collision, a pocket of disturbed gas that never regained equilibrium. But here's the catch: similar impacts on Earth, like the Tunguska event, created temporary atmospheric disturbances that faded within years. Jupiter's cold spot has persisted for at least 3 decades, possibly much longer. Another possibility ties the cold spot to Jupiter's auroras. The planet's powerful polar light shows dump enormous energy into the upper atmosphere, creating waves of heat that ripple toward the equator. Some researchers suggest these waves might interfere destructively at a specific latitude, canceling each other out and leaving behind a zone of unnatural calm, like the silent center of a whirlpool where opposing currents meet. If true, this would mean the cold spot isn't just a weather oddity but a standing atmospheric wave, frozen in place by Jupiter's complex energy dynamics. Yet the most puzzling aspect is the spot's stability. Jupiter's thermosphere is a maelstrom of charged particles and supersonic winds, with temperatures that can swing hundreds of degrees in hours. For a cold region this large to endure, something must be actively refrigerating it, either an unseen atmospheric current siphoning away heat or a mysterious chemical process absorbing energy. The answer might lie in exotic molecules like trihydrogen cations, which could form in the upper atmosphere and act as natural coolant. This isn't just about one odd patch of sky. If the cold spot is indeed a long-lived scar from a comet impact, It suggests Jupiter's upper atmosphere has a memory for violence, a way of preserving traces of catastrophes far longer than we thought possible. And if it's tied to auroral activity, it reveals hidden feedback loops in how energy circulates around gas giants. Either way, this enigmatic chill forces us to reconsider how planetary atmospheres respond to disturbances, both from within and beyond. Until future missions study Jupiter's thermosphere in greater detail, the cold spot remains a quiet, freezing mystery, a ghostly reminder of how much we still don't understand about the giants watching over our solar system. Jupiter spins faster than any other planet in our solar system, completing a full rotation in just under 10 hours, whipping its stormy atmosphere into those iconic bands we see from space. But here's the twist: not all parts of Jupiter rotate at the same speed. The planet's equator races ahead, completing a full spin about 5 minutes faster than its polar regions. This bizarre mismatch, called differential rotation, turns Jupiter into a cosmic turntable with gears that don't quite sync up. How can a single planet have multiple rotation speeds, and what does this tell us about the chaotic dance happening beneath those clouds? The answer may lie in Jupiter's layered interior. Unlike rocky planets with solid surfaces, Jupiter is essentially a giant ball of fluid hydrogen and helium so compressed that they morph into exotic states under the crushing pressure. At the outer layers, where temperatures are only a few thousand degrees, hydrogen behaves like a gas, whipped into frenzy by winds and storms. But dive deeper, and the pressure mounts until hydrogen transforms into a bizarre metallic liquid, capable of conducting electricity like copper. These two realms, the turbulent outer atmosphere and the seething metallic interior, might be rotating at slightly different speeds, like oil floating on water in a spinning bowl. What's truly puzzling is how stable this mismatch has remained over centuries of observations. On Earth, friction between layers would quickly even out any rotational differences, but Jupiter's fluid layers seem to slide past each other with minimal resistance. Some scientists speculate that powerful magnetic fields, generated by the metallic hydrogen layer, act as invisible buffers between these rotating zones. Others propose that heat rising from Jupiter's core creates convection currents so violent they sustain the rotation imbalance, like a cosmic engine stuck between gears. Then there's the wild card: Jupiter's core, or what's left of it. If the planet's fuzzy, partially dissolved core rotates at yet another speed, it could be tugging on the metallic hydrogen layer like an unseen hand, creating ripples in the magnetic field that further complicate the rotation puzzle. Recent measurements from the Juno spacecraft show subtle asymmetries in Jupiter's gravitational field that might trace back to these deep-seated rotational quirks. The implications stretch far beyond Jupiter. If differential rotation can persist for billions of years in a planet this massive, it challenges our assumptions about how fluid bodies behave in space. Exoplanet hunters have spotted similar mismatches in distant gas giants, suggesting this might be a universal feature of massive planets, one that could influence everything from their magnetic fields to the way they form moons. Until we can peer deeper into Jupiter's swirling heart or simulate these extreme conditions in labs, its conflicting rotation rates will remain a tantalizing clue to the hidden forces shaping gas giants across the cosmos. Jupiter's moon collection reads like a cosmic census with glaring gaps in its records. The planet boasts 4 massive Galilean moons: Ganymede, Callisto, Io, and Europa, each large enough to be planets in their own right. Then there's the swarm of tiny irregular moons, some no bigger than a city block, orbiting chaotically in the distant outskirts, but between these extremes. Almost nothing. This absence of mid-sized moons, bodies say 50 to 500 miles across, is one of the solar system's quietest yet most baffling mysteries. Where are Jupiter's missing middle children? One theory points to a violent past of moon-on-moon collisions. Imagine Jupiter's early days, when its orbit may have been crammed with dozens of mid-sized protomoons. As these bodies jostled for space, gravitational tugs from the growing Galilean giants could have sent them careening into each other at catastrophic speeds. Computer simulations show such impacts wouldn't just shatter moons, they'd vaporize them entirely, leaving behind only dust and debris. Some researchers suspect Jupiter's faint rings might be the gravestones of these vanished worlds, their remains ground to powder over billions of years. But there's another, more dramatic possibility. Jupiter itself may have flung its mid-sized moons into the void. The planet's gravity is so monstrous it can act like a cosmic slingshot. Any moon venturing too close during the solar system's chaotic youth might have been hurled outward at escape velocity, condemned to wander interstellar space as a rogue planetoid. Astronomers estimate thousands of such ejected bodies could be drifting between stars right now, silent refugees from Jupiter's dynamical past. Recent discoveries of free-floating orphan moons in deep space lend eerie credence to this idea. The plot thickens when we compare Jupiter to Saturn. While Jupiter lacks intermediate moons, Saturn sports an entire family of them. Mimas, Enceladus, Tethys, all happily coexisting with the planet's larger satellites. This stark difference suggests something uniquely destructive happened in Jupiter's orbit. Perhaps its 4 Galilean moons grew too greedy, hoarding material that might have formed mid-sized neighbors. Or maybe Jupiter's migration through the early solar system, a journey that likely reshaped its gravitational influence, created zones where mid-sized moons simply couldn't stabilize. The answer might lie buried beneath Europa's ice or etched into Callisto's crater's ancient impact records, holding clues to this missing generation. Until we can study these surfaces in greater detail or discover more exiled moons drifting between stars, the gap in Jupiter's lunar lineup remains a haunting reminder of how chaotic planetary systems can be. Sometimes the most telling mysteries aren't about what's present, but what's conspicuously absent. For centuries, astronomers watched Jupiter's white ovals with fascination, great swirls of storm clouds as wide as continents, drifting lazily across the planet's southern hemisphere. Unlike the great red spot's fiery persistence, these ivory-colored tempests appeared and vanished with the unpredictability of bubbles in a boiling pot. Some lasted decades before suddenly merging with neighbors or dissolving into the tawny haze, as if Jupiter's atmosphere couldn't decide whether to cherish or erase them. Their fleeting nature makes them some of the planet's most enigmatic weather features. Why do these giant storms vanish without a trace while others, like the Great Red Spot, rage on for centuries? The mystery deepens when you compare their life cycles. The Great Red Spot is a self-sustaining monster, drawing energy from deep atmospheric currents and possibly even tapping into heat welling up from Jupiter's interior. White ovals, by contrast, seem more fragile, like eddies spun off from jet streams, lacking the deep roots that anchor their crimson cousin. Observations from the late 19th century through the Hubble era show these ovals playing a cosmic game of musical chairs. 3 long-lived white storms dubbed BC, D, and FA swirled in harmony from the 1930s until 1998, when BC and D suddenly collided and merged. Then, in 2000, the combined storm absorbed FA, creating a single massive oval christened BA, which then turned red in 2006, mimicking the Great Red Spot's hue as if donning a disguise. What's truly bizarre is how these mergers unfold. On Earth, when hurricanes approach each other, they either repel or consume one another in chaotic spirals. Jupiter's white ovals, though, perform a slow, graceful dance orbiting a shared center for years before finally coalescing with little visible violence. Some researchers believe anticyclonic storms like these are shielded by invisible barriers formed by Jupiter's alternating wind jets, creating lanes where storms can approach but not immediately collide. Others speculate the ovals exchange material through thin tendrils of cloud, gradually equalizing their energies until they become a single system. The most tantalizing clue comes from their color changes. When oval BA turned red, scientists scrambled for explanations. Some pointed to upwelling gases exposing deeper, darker materials, ammonium hydrosulfide or organic compounds normally hidden beneath upper cloud decks. Others suggested UV radiation might be chemically altering the storm's outer layers, like rust forming on metal. But if that's true, why don't all white ovals undergo this transformation? Why do some vanish while others strengthen and darken? The answer might lie in Jupiter's hidden three-dimensional weather patterns. While the Great Red Spot plunges deep into the atmosphere, white ovals might be shallower, more vulnerable to disruptions in wind shear or temperature gradients. They could be the atmospheric equivalent of surface foam, ephemeral byproducts of deeper currents. When conditions shift, these storms have no reservoir of energy to sustain them, leaving them to fade like ghosts in the cosmic wind. Yet their unpredictability makes them invaluable clues. By studying why some storms thrive and others dissipate, we might unlock secrets about atmospheric stability across the universe, from Saturn's swirling hexagon to the hurricane-laden skies of distant exoplanets. Jupiter's vanishing acts aren't just meteorological quirks. They're fleeting lessons written in cloud tops, reminding us that even the mightiest planets keep some secrets just out of reach. Jupiter's X-ray auroras shatter every expectation of how planetary light shows should behave. While Earth's northern lights paint the sky with gentle greens and purples, Jupiter's polar regions blast out X-rays so intense they briefly outshine the Sun in certain wavelengths, a cosmic fireworks show radiating energies that would sterilize any nearby life. What makes these auroras truly baffling isn't just their power, but their rhythm. They pulse like a heartbeat, flaring predictably every 27 minutes near the North Pole, while the South Pole dances to its own erratic tempo. The secret might lie in Jupiter's magnetic wrestling match with its volcanic moon Io. As Io spews a ton of sulfur dioxide into space every second, Jupiter's magnetic field strips these particles away, stretching them into a donut-shaped plasma torus along the moon's orbit. When solar wind disturbances or Io's own motion kink these magnetic field lines, they snap like overstretched rubber bands, launching charged particles toward the poles at nearly light speed. These particles then slam into Jupiter's atmosphere, and here's where the magic happens. Unlike Earth's auroras, where electrons collide with oxygen or nitrogen, Jupiter's atmospheric heavyweights hydrogen and helium get ionized so violently they emit X-rays. It's like watching a particle accelerator the size of a planet at work. But the plot thickens when you realize solar wind alone can't explain the sheer intensity. Earth's auroras flicker in response to solar activity, but Jupiter's X-ray flares sometimes ignite when the solar wind is calm, suggesting an internal power source. Some researchers point to Jupiter's metallic hydrogen core, where electrical currents generated by the planet's rapid rotation might inject extra energy into the auroral system. Others propose that Jupiter's magnetic field, 20,000 times stronger than Earth's, acts like a giant capacitor, storing energy until it discharges in these dazzling X-ray bursts. The most haunting clue comes from the north-south asymmetry. While the South Pole's X-rays flare unpredictably, the North Pole's 27-minute pulsations are so regular you could set a watch by them. This precision hints at a standing wave pattern deep in Jupiter's magnetosphere, perhaps created by interactions between the magnetic field and plasma currents we can't yet observe. It's as if the planet has an invisible X-ray metronome ticking beneath its storms, conducting an electromagnetic symphony we're only beginning to hear. Understanding these auroras isn't just about solving a Jovian puzzle. It's a window into the behavior of exoplanets and pulsars, where similar magnetic fireworks might play out on galactic scales. Until we send probes capable of surviving Jupiter's radiation belts long enough to map these processes in detail, these X-ray mysteries will continue to pulse in the dark, a reminder that even our solar system's grandest performances still hide their most spectacular tricks. Jupiter's jet streams are the fastest rivers of gas in the solar system, roaring across the planet at speeds that would tear Earth's atmosphere apart. But here's what defies logic: these titanic winds don't stay constant. Unlike Earth's relatively steady trade winds, Jupiter's jet streams accelerate and decelerate without warning, sometimes shifting by dozens of miles per hour over just a few years. It's as if the planet has invisible throttles buried in its clouds, twisting the dials on these atmospheric highways whenever it pleases. These speed changes aren't random. They pulse in strange, planet-wide patterns. Between 2009 and 2020, Hubble observations revealed Jupiter's equatorial jet mysteriously slowing down while mid-latitude winds sped up, as if the planet were redistributing energy on a global scale. Even more bizarre, the Great Red Spot's westward jet has been gaining momentum for decades, like a storm spinning its own engine faster against the flow. Something deep within Jupiter is conducting these winds like a chaotic orchestra, but we're only beginning to hear the music. One leading theory points to Jupiter's interior as the puppet master. The planet's metallic hydrogen core generates immense heat, which bubbles upward in colossal plumes. When these thermal waves reach the upper atmosphere, they might inject energy into specific jet streams, revving them up like turbochargers. Alternatively, deep atmospheric waves similar to Earth's ocean waves but thousands of miles tall could carry momentum between layers, transferring speed from one latitude to another. Imagine ripples in a pond, but where the water itself starts flowing faster just because the waves pass through. The wild card is Jupiter's magnetic field. Charged particles spiraling along magnetic field lines might interact with the ionized gases in the upper atmosphere, creating electromagnetic drag or acceleration in ways we don't yet understand. Recent Juno data found odd correlations between wind speed changes and fluctuations in Jupiter's magnetic field strength, hinting at a hidden dialogue between the planet's interior dynamo and its outer storms. What makes these shifting winds so critical is their connection to Jupiter's banded appearance. Those iconic stripes aren't just cosmetic, they're the visible edges of jet streams in conflict, where winds shear against each other like cosmic fault lines. If the winds change speed, the bands can widen, narrow, or even spawn new vortices. In 2019, astronomers watched as a jet stream between two dark belts suddenly surged, splitting a single cloud band into three distinct sections within months. It's a stark reminder that Jupiter's beauty is born from chaos, a ceaseless negotiation between forces we've only begun to measure. Perhaps the most humbling realization is how little we know about the rules governing gas giant weather. Earth's climate models fail spectacularly when applied to Jupiter, where a lack of surface friction and the planet's own heat production create a system that operates by its own inscrutable logic. Every time we think we've decoded a pattern, Jupiter throws another curveball, like the recent discovery that its wind speeds might be tied to sunlight intensity, despite the planet's internal heat dwarfing solar input. Until we can probe deeper or simulate these extreme conditions in labs, Jupiter's inconsistent winds will remain a masterclass in atmospheric mystery. They challenge our very definition of weather, proving that even the most fundamental forces can behave unpredictably when scaled to planetary proportions. And if a planet this massive can change its winds on a whim, what else might it rewrite in the cosmic rulebook? Deep within Jupiter's churning clouds, a bizarre form of precipitation falls. Not water hailstones, but slushy balls of ammonia and water ice scientists call mushballs. These strange, half-melted projectiles grow to the size of basketballs as they plunge through the atmosphere, solving a mystery that's puzzled researchers for decades. Why Jupiter's upper layers appeared curiously short on ammonia despite the gas being abundant deeper down. The discovery came when NASA's Juno spacecraft detected radio signals consistent with electrical discharges, not from lightning, but from the static electricity generated as these mushy hailstones collided. Unlike Earth's hail, which forms in thunderstorm updrafts, Jupiter's mushballs begin life in an exotic process unique to gas giants. At altitudes where temperatures hover around -150 degrees Fahrenheit, ammonia acts as an antifreeze, mixing with water vapor to create a gooey ammonia water, snow. As these sticky flakes tumble through layers of hydrogen and helium, they accumulate more material, growing into massive, spongy ice balls that can descend over 300 miles before vaporizing in the planet's scorching depths. This explains Jupiter's disappearing ammonia. Traditional models assumed the gas would rise evenly through the atmosphere, but mushballs act like atmospheric conveyor belts, trapping ammonia in their slushy cores and dragging it downward faster than currents can replenish it. Some regions might experience literal ammonia droughts, periods where the gas is temporarily scrubbed from upper cloud decks until fresh supplies well up from below. The implications ripple beyond chemistry. These falling mushballs could seed Jupiter's lower atmosphere with ingredients for complex organic molecules, essentially raining probiotic material into zones where temperatures and pressures might foster unexpected chemistry. Even more intriguing, similar processes might occur on other gas giants, meaning mushball storms could be a universal weather phenomenon in hydrogen-rich atmospheres across the galaxy. Yet the biggest surprise is how long this went undetected. For decades, scientists assumed Jupiter's ammonia distribution would follow predictable patterns until Juno revealed stark variations that made no sense under old models. Only by combining microwave radiometer data with lightning detections did the pieces click into place. What looked like missing ammonia was actually being hidden in plain sight, disguised as slushy hail. It's a humbling reminder that even the most studied planets can harbor secrets waiting to be uncovered, sometimes in the most delightfully strange forms. On Earth, hurricanes are like boxers past their prime. They burn bright but fade fast, especially when they hit land. The friction from mountains, forests, and even city skylines acts like a brake, sapping their energy until they collapse into harmless rain showers. Jupiter's storms laugh at such weakness. Without a solid surface to grind against, cyclones on this gas giant spin freely, feeding off atmospheric currents that stretch tens of thousands of miles deep. It's the difference between a pinwheel stuck in mud and one whirling in a vacuum. Jupiter's tempests face no obstacles, no friction, nothing to slow their rage except the occasional clash with another storm. This lack of surface friction isn't just a minor detail, it rewrites the rules of meteorology. Earth storms draw energy from warm ocean waters, but once they leave that fuel source, they're doomed. Jupiter's storms, though, tap into something far more relentless, heat welling up from the planet's scorching interior. Imagine a hurricane that could plunge its roots into a volcanic furnace, constantly reheating itself as it churns. That's the hidden advantage of Jupiter's fluid nature. Energy isn't just skin deep. The Great Red Spot isn't a surface storm. It's a towering vortex that may extend 200 miles downward, possibly even deeper, threading into layers where hydrogen behaves like liquid metal. Even collisions play out differently in this frictionless arena. When two storms meet on Earth, the result is messy and unpredictable. One might absorb the other, or they could spiral apart. On Jupiter, mergers happen with eerie elegance. White ovals drift together for years, orbiting a shared center like celestial dancers, before finally blending without the violent turbulence you'd expect. This grace comes from the absence of surface interference. There's no land to disrupt the flow, no topography to steer storms off course. The atmosphere operates like a perfectly tuned fluid dynamic lab, where vortices obey mathematical principles rarely seen on smaller worlds. Yet the strangest consequence of Jupiter's surface-less design isn't just storm longevity, it's storm geometry. Earth's hurricanes are roughly circular, shaped by the Coriolis effect and random atmospheric noise. Jupiter's cyclones, though, arrange themselves into freakishly precise polygons. The North Pole's octagon of storms and the South Pole's pentagon defy natural odds, maintaining their geometric formations with military discipline. Some researchers suspect this order emerges from something called beta drift, where Jupiter's rapid rotation carves invisible pathways in the atmosphere, herding storms into stable, symmetrical patterns. Without landmasses to create chaotic eddies, these mathematical ideals can play out on a planetary scale. The lesson here is humbling. Jupiter's storms aren't just bigger versions of Earth's, they're a glimpse into an alien physics where fluid dynamics operates without the brakes our planet provides. It's a reminder that the same universal laws can yield wildly different outcomes when you remove something as simple as solid ground. And if we ever hope to understand the tempests raging on distant exoplanets, Jupiter's endless cyclones offer the closest manual we have, a textbook written in wind and fire waiting to be decoded. Jupiter's clouds paint a mesmerizing palette across the sky, creamy whites, deep russet browns, and that iconic crimson splashed across the great red spot. But here's the cosmic conundrum. Lab experiments can't quite replicate these exact hues, leaving scientists to play detective with a color mystery that stretches across millions of miles. What brews in Jupiter's atmosphere to create such vivid shades, and why does it stubbornly resist our attempts to recreate them on Earth? Start with the planet's most famous feature, that blood-red tempest swirling for centuries. The leading suspect, ammonium hydrosulfide, a compound that forms when hydrogen sulfide and ammonia react under pressure. In labs, when scientists cook up this chemical and expose it to ultraviolet light, it darkens into reddish-brown tones close but not quite matching the spot's dramatic scarlet. Some researchers argue the missing ingredient could be organic molecules like tholins, complex compounds forged when solar radiation bakes simple hydrocarbons. These tholins, found on Pluto and Titan, produce rusty hues in experiments, but Jupiter's version seems uniquely intense, as if the planet's atmosphere is amplifying the effect. Then there's the puzzle of Jupiter's white zones, regions where gas rises, cooling into bright ammonia ice clouds. These should be pure white, yet they often carry a faint yellowish tint. The culprit might be phosphorus, sublimated from deeper layers and mixed into the upper clouds like dye in fabric. Or consider the planet's tawny belts, where sinking air reveals warmer, darker layers. Here, mysteries compound. Traces of sulfur and carbon compounds could be interacting in ways we haven't yet imagined, creating complex polymers that absorb specific wavelengths of light. The real challenge lies in Jupiter's extreme environment. To truly replicate its colors, we'd need to simulate pressures 1,000 times greater than Earth's surface, temperatures swinging from -200 to thousands of degrees, and constant bombardment by charged particles. Even then, Jupiter's atmosphere isn't static. It's a churning laboratory where chemicals mix, rise, sink, and transform over decades. The great red spots deepening red in recent years hints that these processes are dynamic, with UV radiation or atmospheric circulation possibly concentrating chromophores like a slow cosmic dye bath. Perhaps most tantalizing is the role of unseen chemistry. Lightning storms might be sparking reactions that create exotic molecules, while auroral particles bombarding the poles could induce phosphorescent glows invisible to our telescopes. And what if Jupiter's colors aren't just about composition but structure? The way cloud particles scatter light, their size, shape, and layering could turn mundane chemicals into visual marvels like sunlight filtering through stained glass. This isn't just about aesthetics. Jupiter's colors are cosmic fingerprints, clues to the planet's composition, weather patterns, and even its formation history. Cracking this code could help us decode the atmospheres of exoplanets, where similar pigments might hint at hidden chemistry. Until we can probe deeper or recreate Jupiter's violent beauty in labs, its palette remains a masterpiece, one we're still learning to see. Shadows should be cold, that's basic physics, right? When sunlight gets blocked, temperatures drop, except on Jupiter, where the rules seem to twist into knots. Scientists have spotted something downright bizarre. Certain shadowed regions on the planet are actually warmer than nearby areas bathed in sunlight. It's as if stepping under a cosmic umbrella somehow turns up the heat instead of offering relief. This hot shadows phenomenon flips intuition on its head, revealing just how alien Jupiter's energy dynamics truly are. The key might lie in gravity waves, not the cosmic ripples from black holes, but massive atmospheric surges that ripple through Jupiter's fluid layers like ocean waves through water. Here's how it works. When storms or jet streams disturb the upper atmosphere, they generate vertical waves that plunge deep into the planet's interior. As these waves descend, they compress and heat the surrounding gas, kind of like how a bicycle pump warms up when you rapidly press the handle. When these heated parcels of gas rise back up, they can warm shadowed regions from below, creating thermal hotspots where logic says there should only be chill. But storms are the real puppet masters here. Jupiter's cyclones act like enormous atmospheric mixers, churning heat from the planet's scorching interior and redistributing it with terrifying efficiency. The Great Red Spot alone may be funneling heat upward like a colossal chimney, creating invisible thermal plumes that snake through the atmosphere. When these plumes intersect with shadowed zones, say where a moon like Europa casts its silhouette, they can override the cooling effect of blocked sunlight, swamping the area with warmth from below. It's a bit like sitting in the shade of a tree, only to feel heat radiating up from underground hot springs. The numbers are staggering. Some shadowed regions measure over 50 degrees Fahrenheit warmer than their sunlit surroundings, a temperature inversion that makes Earth's weather quirks seem tame. Infrared images reveal these anomalies as ghostly blooms of heat, often aligned with storm systems or turbulence in Jupiter's deeper cloud layers. Researchers suspect this heat isn't just leaking out randomly. Jupiter's banded winds might be channeling it along specific atmospheric highways, directing warmth to unexpected destinations like a planetary heating system gone rogue. What makes this discovery so revolutionary is how it challenges our ideas about energy flow in gas giants. Earth's weather is primarily driven by sunlight, but Jupiter's hot shadows prove the planet's own internal furnace plays an equal, if not greater, role. This could explain why some storms persist for centuries. They're not just drawing energy from the sun, but tapping into a deep planetary battery of heat. Future probes might uncover even stranger thermal oddities like cold spots in sunlight or pulsating temperature waves we can't yet imagine. For now, Jupiter's hot shadows remain a masterclass in atmospheric defiance, a reminder that even the simplest assumptions can crumble when faced with a planet that rewrites the rules as effortlessly as it casts a warm, impossible shade. Jupiter's stratosphere holds a wind mystery that defies everything we know about atmospheric layers. While the lower cloud decks churn with planet-encircling jet streams, the upper stratosphere plays by its own rules, hosting bizarre wind patterns that reverse direction suddenly and without explanation. The most glaring anomaly, a narrow band of superfast winds straddling the equator, roaring eastward at speeds unmatched anywhere else in the solar system's upper atmospheres. This high-altitude jet screams along at over 600 miles per hour, yet just 20 miles below, equatorial winds crawl westward like sluggish river currents. How can two layers of the same atmosphere, separated by such a thin slice of altitude, move in opposite directions with such violence? The first clue comes from temperature. Jupiter's stratosphere is oddly warm, not just from sunlight but from some hidden heat source cooking the gas from within. Auroras near the poles dump tremendous energy into these upper layers, but the equatorial jet lies too far away to benefit from that polar furnace. Some scientists point to gravity waves, not the space-time ripples of astrophysics, but massive pressure waves generated by storms below. As these waves crash upward like ocean breakers hitting a cliff, they might dissipate energy into the stratosphere, creating turbulence that organizes into jets. Others suspect a global thermospheric circulation, a planet-wide conveyor belt where gases heated at the poles migrate equatorward, then sink, driving winds as they go. The wild card is Jupiter's infamous Great Cold Spot, a high-altitude chill zone that might be siphoning energy from surrounding winds like a cosmic eddy. Recent observations show this frigid vortex pulsing in sync with stratospheric wind shifts, hinting at a connection deeper than coincidence. It's as if the entire upper atmosphere is a Rube Goldberg machine of energy transfers, where heat from auroras, momentum from storms, and waves from deeper layers conspire to create a wind pattern no single process can explain. What makes this puzzle critical is how it mirrors challenges in exoplanet research. Distant, hot Jupiter worlds show similar mismatches between upper and lower wind speeds, suggesting this might be a universal gas giant quirk we're just beginning to decode. If Jupiter's stratospheric winds arise from some combination of wave dynamics and internal heating, that same recipe could apply to bloated exoplanets orbiting close to their stars. Until we can send atmospheric probes to parachute through these enigmatic layers, or until telescopes powerful enough to map exoplanet winds come online, this high-altitude riddle remains a masterclass in how little we truly grasp about fluid dynamics at planetary scales. Perhaps the most humbling realization, Jupiter's stratosphere might be showing us the limits of Earth-bound meteorology. Our weather models, honed on a world with oceans and mountains, fail spectacularly when applied to a fluid realm where winds have no surface to scrape against and energy comes as much from within as from sunlight. Every new observation peels back another layer of complexity, proving that even after centuries of study, Jupiter's sky still writes textbooks we're only starting to read. Ganymede shouldn't exist, at least not as we know it. Jupiter's largest moon is a cosmic contradiction, sporting a density so low it practically floats compared to similarly sized worlds. Clocking in at just 1.9 grams per cubic centimeter lighter than Earth's moon by nearly 40%, Ganymede's featherweight composition hints at something extraordinary lurking beneath its icy shell. A hidden ocean stretching hundreds of miles deep, containing more liquid water than all of Earth's seas combined. How does a moon this massive, larger than Mercury and Pluto, end up with such a puzzlingly low density? The answer lies in its layered architecture. Imagine a cosmic snow globe with three distinct tiers, a metallic core smaller than expected for its size, a sprawling mantle of rock and ice, and that staggering subsurface ocean sandwiched in between. This aquatic layer isn't some shallow pocket. It's a vast global sea up to 600 miles thick, kept liquid by gravitational kneading from Jupiter's tidal forces and radioactive decay in the moon's interior. The sheer volume of water dilutes Ganymede's overall density, making it behave less like a solid world and more like a planetary sponge. Yet the real shocker isn't just the ocean, it's Ganymede's magnetic field. No other moon in our solar system generates its own magnetism, yet Ganymede's dances with Jupiter's in an intricate celestial waltz. Earth's magnetic field comes from churning molten iron in its core, but Ganymede's core is too small and likely too cool to power such a dynamo conventionally. The secret might lie in that subterranean ocean. Salt water conducts electricity, and as it sloshes beneath the ice stirred by Jupiter's gravity, it could generate electric currents strong enough to produce a secondary magnetic field, a planetary-scale battery fueled by tidal friction. This duality creates a magnetic fingerprint unlike anything else. When NASA Galileo spacecraft flew by in the 1990s, it detected Ganymede's field embedded within Jupiter's far mightier one, like a whisper fighting to be heard in a hurricane. The moon's magnetism is so delicate that it flickers in and out of detection as it interacts with Jupiter's plasma torrents, creating auroras that skitter across its poles like ghostly fireflies. The implications ripple far beyond our solar system. If a moon with Ganymede's structure can sustain both a deep ocean and a magnetic field, what might lurk beneath the ice of exoplanets orbiting distant stars. Its existence forces us to reconsider the recipe for habitable worlds, proving that liquid water and protective magnetic shields aren't exclusive to planets. Ganymede's quiet defiance of expectations makes it more than just Jupiter's largest moon. It's a blueprint for how seemingly frozen worlds might hide the very ingredients for life beneath their surfaces. Io isn't just a moon, it's a planetary pressure cooker spewing lava fountains taller than Mount Everest and painting its surface in rivers of molten sulfur. No other world in our solar system erupts with such violence, generating enough heat to power over 400 active volcanoes. Yet this tiny moon, barely larger than Earth's own, orbits so far from the Sun that its surface should be frozen solid. The secret to Io's fiery tantrums lies in a cosmic tug-of-war between Jupiter's gravity and the stubborn resilience of rock itself. Jupiter's gravitational grip on Io is relentless. The moon orbits so close that the planet's tidal forces stretch and squeeze its interior like a rubber ball caught in a vise. But here's the twist: Io doesn't orbit alone. Its sister moons Europa and Ganymede tug at it with their own gravity, forcing Io into an elliptical path that sends it alternately diving toward Jupiter and swinging away. This irregular orbit means the tidal forces vary constantly, stretching Io one moment, compressing it the next. The resulting friction heats its rocky interior to thousands of degrees, melting solid rock into magma that erupts through countless volcanic vents. It's like kneading dough until it grows warm from the friction, except on a scale where the dough is a moon and the heat could melt steel. Yet even this explanation might not account for Io's staggering volcanic output. Simple tidal heating models predict activity maybe a tenth of what we observe. Some scientists suspect Io's interior holds hidden reservoirs of volatile compounds, sulfur dioxide, or even water, trapped beneath the crust. When these materials heat up, they could expand explosively, supercharging eruptions beyond what pure rock friction could produce. Others propose that Io's mantle isn't uniformly viscous. Pockets of partially molten rock might concentrate tidal stress like weak spots in an overinflated balloon, creating localized infernos that vent far more lava than expected. The wildest theory: Io's heat might not come entirely from tidal forces. Jupiter's magnetosphere bombards the moon with charged particles, inducing electric currents in its iron-rich core. These currents could generate additional ohmic heating, essentially turning Io into a planetary-scale toaster coil. Combine this with tidal stretching, and you've got a moon cooking from both the inside and outside simultaneously. Whatever the precise mechanism, Io's eruptions have reshaped its surface into something out of a nightmare. Lava lakes the size of Texas bubble beneath crusts of cooling rock, while plumes of sulfur dioxide gas shoot 300 miles into space, high enough to briefly escape Io's gravity before snowing back down as yellow-white frost. The moon's very topography recoils from this violence. Some volcanic depressions collapse so rapidly they leave behind steep-sided pits called Planetary, while relentless lava flows erase impact craters almost as soon as they form. The implications stretch beyond our solar system. If tidal heating can turn a small moon into a volcanic hellscape, what might it do to exoplanets orbiting close to their stars? Io's ceaseless eruptions challenge our assumptions about where geologic activity can exist, proving that even in the cold outer reaches of a star system, unimaginable heat can lurk beneath the surface. Until we land a probe on those burning plains or simulate these extreme conditions in labs, Io's furnace will keep burning as one of the solar system's most spectacular anomalies. A world where gravity's invisible hands mold not just orbits but landscapes of fire. Europa's icy crust hides what might be the solar system's most tantalizing secret: a global ocean with twice the volume of all Earth's seas combined, swirling beneath just 10 to 15 miles of frozen water. But what makes this hidden realm truly extraordinary isn't just the presence of liquid water. It's the chemical cocktail that might be brewing in those lightless depths. Unlike Earth's oceans, which exchange gases freely with the atmosphere, Europa's sea exists in perpetual darkness, sealed beneath an ice shell and potentially interacting directly with a rocky seafloor. This setup creates conditions that could transform simple molecules into something far more intriguing, especially if hydrothermal vents spew mineral-rich fluids into the mix, just as they do along Earth's mid-ocean ridges. The first clues to Europa's exotic chemistry streak across its surface in the form of reddish-brown fractures, jagged lines staining the otherwise pristine ice like rust-colored veins. Spectroscopic analysis suggests these discolorations contain salts like magnesium sulfate, possibly mixed with organic compounds known as tholins. These complex molecules form when simple hydrocarbons like methane are bombarded by radiation, creating reddish, tar-like substances. But here's the mystery. If Europa's ocean is locked beneath impenetrable ice, how did these materials reach the surface? The answer might lie in brine upwelling, pockets of salt water from below percolating upward through cracks in the ice, carrying chemical traces of the hidden ocean like messages in a bottle. Then there's the question of energy. Earth's deep-sea vents thrive on chemosynthesis, where microbes convert minerals into energy without sunlight. Europa could host similar ecosystems powered by hydrothermal activity at its seafloor. Jupiter's relentless tidal forces likely keep the Moon's interior flexing, generating enough heat to sustain volcanic vents where superheated water, perhaps exceeding 800 degrees Fahrenheit, leaches minerals from surrounding rock. Lab experiments show that under such conditions, water and rock can produce hydrogen gas, a potent energy source for microbial life. Even more provocatively, Europa's ocean might contain oxidants created when radiation splits surface ice, which could then seep downward through fractures, creating a chemical gradient ripe for exploitation by living organisms. The wild card is pH. Earth's oceans are mildly alkaline, but Europa's could range from acidic to highly alkaline depending on mineral interactions at its seafloor. Recent models suggest its waters might be rich in chlorides rather than sulfates, creating a chemistry more akin to Earth's salt lakes than its open oceans. This could influence everything from the stability of organic molecules to the types of hypothetical life that might exist there. Some researchers even speculate that Europa's ocean might contain ballistic organics, complex carbon compounds launched from its sibling moon Io's volcanic plumes, which then rain down onto Europa's surface and eventually migrate into its subsurface sea. Yet the most tantalizing possibility remains those reddish stains. If they truly contain organic material, are we seeing the frozen remnants of a deep-sea biochemical process? Or merely sterile chemical reactions playing out over eons? Upcoming missions like NASA Europa Clipper, equipped to analyze surface chemistry in unprecedented detail, might finally offer answers. Until then, Europa's hidden ocean remains a cosmic petri dish, a laboratory where chemistry could be performing experiments we've yet to imagine, all beneath a shell of ice that's both a barrier and a tantalizing window into the unknown. Jupiter's faint rings shouldn't be this orderly. Unlike Saturn's dazzling loops that ripple with complex waves and braids, Jupiter's dark hoops maintain razor-sharp edges as if trimmed by cosmic scissors. The architects behind this precision, two tiny moons named Metis and Adrastea, each no larger than a small city, yet wielding gravitational influence far beyond their size. These so-called shepherd moons orbit perilously close to the ring edges, their gentle tugs acting like celestial traffic cops that herd stray dust particles back into formation. Every time a wandering grain drifts too far outward, Metis gives it a gravitational nudge inward. Venture too close to Jupiter, and Adrastea's pull steers it back toward the pack. The result is a ring system with edges so crisp they'd put a diamond cutter to shame. But here's the puzzle. Saturn has shepherd moons to Pan, Daphnes, and others, yet its rings overflow with intricate structures like spokes, knots, and propeller-shaped gaps. Why do Jupiter's rings remain stubbornly simple despite similar forces at play? The answer may lie in what these rings are made of. Saturn's brilliant bands consist mostly of reflective ice crystals that amplify subtle gravitational interactions, making every moonlet's fingerprint visible. Jupiter's rings, by contrast, are built from dark, sooty debris, likely pulverized remains of shattered moons or comet impacts. These charcoal-like particles don't respond to subtle nudges the way ice does. They require brute force sculpting from nearby moons. The timing of impacts also plays a role. Jupiter's 4 inner moons, Metis, Adrastea, Amalthea, and Thebe, exist in a continuous demolition derby, bombarded by micrometeorites that blast fresh dust into orbit. This constant replenishment means the rings never have time to develop fine detail before new material washes over existing patterns. Saturn's rings, older and more stable, preserve delicate formations like a slow exposure photograph, while Jupiter's resemble a chalkboard perpetually wiped clean and rewritten. Yet the real mystery isn't why Jupiter's rings are simple, it's how the shepherds avoid catastrophe. Metis orbits just 800 miles outside the main ring, whipping around Jupiter every 7 hours at speeds that would vaporize most spacecraft. At this breakneck pace, the moon should be plowing through enough ring debris to either disintegrate or carve a gaping hole. Instead, it glides along the edge like a surfer riding a wave, maintaining perfect harmony with the chaos it helps contain. Some researchers speculate electromagnetic forces might be at play, charged dust particles repelling each other just enough to prevent catastrophic collisions. Others suggest Metis and Adrastea act like snowplows, their gravity creating density waves that push debris away before contact occurs, the most haunting possibility. These orderly rings might be fleeting. Without constant dust replenishment from those battered inner moons, Jupiter's dark halo could vanish within decades, a whisper-thin marvel existing only as long as its shepherds keep dancing on the edge of destruction. From the eternal fury of the Great Red Spot, a storm older than modern science itself, to the planet's bizarre lopsided magnetism that defies every symmetry we thought governed planetary fields, Jupiter remains a cosmic rebel, rewriting the rules as effortlessly as it reshapes storms. How does a cyclone larger than Earth rage for centuries without burning out? Why does Jupiter's magnetic field look like it was assembled by someone who lost the instruction manual? Even the planet's very core seems to be playing hide and seek, dissolving into a fuzzy enigma that challenges our understanding of how worlds are built. And let's not forget those geometric storms huddled at the poles, or the X-ray auroras pulsing with the precision of a metronome. Each mystery a reminder that Jupiter isn't just a planet. It's a laboratory for physics at scales we can barely imagine. What makes these puzzles so thrilling isn't just their strangeness, it's how they force us to rethink the fundamentals. Jupiter's refusal to conform reveals gaps in our knowledge, from fluid dynamics to planetary formation, pushing scientists to craft theories as wild as the phenomena they're trying to explain. Maybe the Great Red Spot isn't just a storm but a self-sustaining atmospheric engine. Perhaps that lopsided magnetism hints at a churning ocean of metallic hydrogen behaving in ways no lab can replicate. Every oddity whispers a question. If we've misjudged something as basic as how gas giants store heat or generate magnetic fields, what else might we have wrong about the universe? The next chapter of this cosmic detective story is already being written. Missions like Europa Clipper won't just explore Jupiter's icy moon, they'll study the planet itself, peeling back layers of mystery with instruments far sharper than anything we've sent before. Could hidden oceans inside Ganymede or Europa hold clues to Jupiter's chaotic magnetism? Will we finally catch the Great Red Spot in the act of vanishing or transforming into something new? One thing's certain, the more we learn, the more Jupiter will surprise us. So tell us which of Jupiter's riddles keeps you up at night. Is it the missing core, the eerie precision of those polar cyclones, or something we didn't even cover? Drop your favorite mystery in the comments, and while you're there, let us know what you think Europa Clipper might uncover. The universe's greatest classroom isn't here on Earth. It's hanging in the night sky, striped in ochre and cream, waiting for us to decode its secrets. And with every mission, every telescope observation, we're getting closer. Until then, keep looking up, because Jupiter's certainly not done keeping